Data is the lifeblood of science. Our models and theories are narratives constructed from what we can see and from what we can observe of nature. As tools change, so does our narrative. For Christopher Columbus, for example, in 1492, the universe was a very, very different place from today, or even from Isaac Newton in the late 1600s. In the early 17th century, the telescope entered astronomy for the first time. Up to then, everything was naked eye. We have seen how Tycho Brahe had challenged Aristotelian knowledge with his observations of the new star of 1572 and of the Great Comet of 1577. Brahe was able to do this because he could see better than everyone else before him. His instruments allowed him to do that. The same with Galileo Galilei in Italy. In 1609, when he pointed the telescope to the moon, he saw a world with mountains, with craters and valleys, a world that looked much more like Earth than with a perfect ethereal sphere. Then, when he pointed the telescope to Jupiter, he discovered 4 of its large moons circling around it. If Jupiter, a planet, can have moons like Earth, what made Earth so special? Once again, a new instrument allowed people to see better and farther, creating serious trouble for those who believed in the Aristotelian worldview. Galileo did the same with his study of motion. He wasn't convinced by Aristotle's explanation of gravity as a natural motion for earthly things to fall down. He started experiment with pendular motion and letting balls roll down inclined planes to measure how long they took and what factors affected their motion. His results changed forever the way we understand gravity and motion. Galileo decided to shock everyone and took his experiment on free fall to the top of the Tower of Pisa. According to his biographer Viviani, he dropped different objects from the tower at the same time. A wooden ball and a much heavier lead ball, both of the same size. The result? They hit the ground at the very same time, so proving that Aristotle was wrong, because for Aristotle, the heavier ball should hit the ground faster. Gravity, or the acceleration it causes on falling objects, is independent of their mass, a fundamental result in physics. So inside this plastic cylinder, I have 2 objects. I have a quarter and I have a piece of paper, a yellow piece of paper, shaped as a quarter. And this experiment is an experiment on free fall. Now, if I let these 2 objects fall, what do you think will happen? Once more. So as you can see, the coin came down first before the piece of paper. So now I'm going to connect this cylinder to a vacuum pump, which is going to suck the air out of the cylinder. Okay, so hopefully the vacuum pump did its job and sucked most of the air, because it can't suck all the air, out of the tube. So let's see what happens. I'm going to detach the vacuum pump, and I'm going to repeat the experiment of free fall. What do you think will happen? Ready, set. So as you have seen, in the absence of air, both objects fall exactly at the same rate. It doesn't matter how heavy they are. So this is telling you something about the nature of reality, where without the air, we see something completely different from what the experiment with the air. Nature can be subtle. You have to look beyond appearances. And that's what Galileo figured out 400 years ago without the vacuum pump. The Galileo experiment of free fall was repeated on the moon by astronauts of the Apollo 15. Galileo found the first laws of motion on Earth, how gravity accelerates falling things without caring about their mass. To do this, he devised amazing experiments that allowed him to answer his questions with precision. This was something radically new, very, very different from the arguments of philosophers, to use precise experiments to study how nature works. And if this wasn't enough, Galileo's astronomical observations seriously undermined the Aristotelian worldview. After thousands of years of an Earth-centric cosmos, a new physical reality was about to be born.